Welcome to the review of the new eHydro scraper class. This is a complete rewrite over the old one, so we have self-contained in a single package three classes who work together to scrape the feature catalog from the Army Corps' remote server. And so that's going to go through our eHydro scrape class, where it's going to process those records or really just download them into an S3 catalog hosted on a MinIO object store. So it's a locally hosted S3 API that we can access these data with. And then from there, the other class, the processing class, eHydro process, will pull in those records. It will identify the changes between the records in the object store as compared to the last scrape, which has snapshotted itself in Postgres. So it will compare those two tables to see what's new. So anything that's been added, removed, or modified, and modified is defined by the zip file's hash has changed. Now, not everything has a hash record, so we have some extra logic to process that. But once we've done our change detection, we're then going to go through spatial analytics, and we're going to identify which of the new incoming surveys are located within which of the processing branches. And so 100% of this workflow is going to be executed inside of a DuckDB connection object. So DuckDB will attach to the Postgres instance. It will also manage the S3 object store. And as needed, it can also send data back and forth between Pandas data frames or NumPy arrays. It doesn't matter at that point. So DuckDB is extremely flexible. It's also more performant than doing this with something like Pandas alone, because DuckDB is immune to Python's global interpreter lock, which means it can multi-thread without any additional Python packages or coding. It's just automatically going to happen. So the spatial analysis is the biggest benefit here. And with the recent versions of DuckDB, with 1.4 and above, the spatial analytics and the interaction between geometries in Postgres and S3 object stores has been mitigated. Let's take a look at the scraper class first. One of the more important things about this is the ingress query. Now, the Army Corps' remote server will provide two resources for us. One is the feature catalog itself, and the other is a hash catalog, which contains a listing of zip files and the MD5 checksum as a hash. And so that's a mapped file that we can bring in and compare to our feature server. Unfortunately, there's not a one-to-one correlation here. So not every feature in the feature server has an entry in the hash catalog. So there will be cases where we don't have a zip file with a hash, for example, or even a zip file. So as we join the hash table to the feature table, as indicated by the prefixes before each of these field names, we do have the ability to perform some extra steps on the ingress query. So one of them would be staging placeholder fields for some of the co-survey specific things, such as NOAA division or processing branch. But also, if we have additional mappings, such as we do here with Army Corps headquarters, there's a map for headquarter to USC ACE district. We can also populate that field. Well, we can add that field and populate that field. A more significant example of that would be with respect to the best XYZ file. So the way this works is we have two fields in the feature catalog. We have the source data location, which is the URL to the downloadable zip file. And we have source data content, which gives us a listing of files that we can expect to find within that zip file. Now, there's an interesting hierarchy that we're after here. There will be sometimes several XYZ data files within the source data content listing. And so we want to rank them based on sounding density and then only extract the one that we're going to feed or the one that we're going to identify for data processing. And so we can structure that on our ingress query as well. And that's what's happening here. So while we're loading data into our object store, we're already doing some metadata enrichment. Similarly with the zip file, if the zip file wasn't in the hash catalog, then on this join query, that would produce a null. But we do have the URL from the source data location, And the end of that URL is the zip file name as well. So we can actually extract that as needed and populate that field as well. So now switching over to the feature catalog itself, just to confirm, the Army Corps currently says there are 114,823 available surveys in their feature catalog, and most of these are going to have a zip file and a hash record in their hash catalog. So we're going to go ahead and walk through. I've already done a scrape here, so I'm just going to switch over to that. And we have a Jupyter notebook set up to demonstrate how to exercise these three classes. And also to note is I have the credentials set up for offsite and on-prem. As this is an entirely containerized process, it's portable now. It does work and it runs successfully on NBS Linux 1, but it's also doing this on my local infrastructure. So I wanted to demonstrate that just to say this is already ready to be deployed in the cloud. A scrape takes about 10 minutes or so to get all 114,000+ records, mostly because of bandwidth limitations and network bottlenecks. The feature server only allows one active connection at a time, so you're not going to pull this down in parallel. So it takes about 3 to 5 seconds per 1,000 records, and we have 100,000+ records. So that translates to a few minutes, and then we're going to merge those catalogs and we're going to bring them in. And once we've done that, we're going to go through the change detection, which means loading the object store and the Postgres tables into memory. Also, at this time, it's convenient just to load from the regions JSON. Go ahead and chase down all the references in there. Because JSON files can be DuckDB tables as well. So we have a quick way to go ahead and get those geo packages and extract those polygons and prepare them for the spatial analytics later. That's pretty instantaneous. But then to do the change results, once we've loaded everything into memory, and to do the change results, took under 5 minutes. So it takes longer to download the data than it does to actually buffer it into memory and do the change detection. And it also took 5 minutes because it did have to download some data. So it found 597 new files and one modified file. And the reason it found so many was because I deleted all records in our Postgres snapshot since October 15th. So we've got a few weeks of data that we're expecting changes to come in for. And that was just for demonstration. So it did go ahead and download all of the zip files. If it needed to download it, it did. If it already existed in our object store and its hash checked out, it skipped it. So sometimes it downloads it and sometimes it doesn't, and that'll take a few minutes. Once we've done that, this is the most impressive part of the whole workflow. We're going to process all 44 active processing branches by comparing all 100,000+ features in the object store catalog to all processing branches in one giant stack. That took about 40 seconds. So it was able to go through each processing branch and identify how many surveys were in that branch and how many of those surveys were in our change detection results. And so from there, we're able to actually create a running tally. So for the entire feature catalog, we can break it out now by our processing branches. So we'll count the number of surveys per branch, and then the number of those surveys having a valid geometry, a valid data file that we can feed to Fuse, and a valid checksum, meaning that data hasn't changed and it matches what's on the feature catalog server. We're also going to perform these same 3 checks on the data that's been identified as new data. So if the new data has a valid geometry, data file, and hash, then we'll mark it as usable. If it does not, as it does happen sometimes, then we'll see there's a discrepancy here in our new data. And so what we're currently doing in our legacy setup is we're passing all the new surveys in and then doing additional checks in the data pipeline, which we don't need to do that here. We really quickly, in just a couple of seconds actually, have identified that there are 3 surveys for this processing branch, for example, that should be withheld because they're probably going to be updated by the time we scrape this catalog again. So they are in the process of adding either geometry data or the valid hash checksum to it. So once we've done that, we really just want to snapshot these things back to Postgres. And that sets us up for the next scrape at a later time where we'll have a different change result. And so at this point, we have all of the changes in the spatial analytics done, and we have 2 copies of the catalog, and we have it in 2 versions. So we actually have the raw catalog with slightly enriched metadata. We also have the filtered catalog with significantly enhanced metadata. And we have that in both our object store and in Postgres. And now having it in Postgres is very convenient because that's the most consumable form for QGIS. So this benefits our operations side the most, whereas the object store is most beneficial for programming and automation. So we know that we have the same data in both places, we have it in different versions, and we have all of the information we need to set up a data pipeline. So I just want to show you here that the feature catalog is indeed the entire catalog. And if I now turn on the filtered catalog and turn off the featured catalog, you'll see that we have significantly less because we only had about 500, 600 records. And we can also see that they are specific to our co-survey divisions and processing branches. And so if something is interior to the US, for example, it may not be related to the National Bathymetric Source Program. That's automatically been taken care of here. So if we're going to look in some of these just to compare what's in these files, let's go ahead and pull one of these forward. And we can see this is coming from the raw catalog. So we're not able to populate some of the NOAA specific stuff in here, but we did set it up, if you remember from our ingress query. Also, the times are in epoch times in milliseconds. And so we'll convert that in our filtered results. But we do have the addition of a GeoJSON link, which is going to be interesting for discussion with respect to Fuse. We're currently processing data into a geo package. So each of the features in here gets extracted from the catalog and packaged as a geo package, and that's what Fuse uses. But we have the GeoJSON and we have the geometry both in the object store and in Postgres already. So we really don't need to read that same geometry from a geo package. That part seems to be a bit redundant, maybe can go away. So let's at the same time turn on one of our new records and look at what's in those. Okay, so here we go for a feature that's in the filtered catalog. We can see we now have human readable times when we've processed the NOAA division and processing branch as well. And also it's nice to point out that we have the best XYZ here. We can see that we were lacking a underscore full or an underscore a.xyz for this particular one. Maybe if we bounced around, we can find a different scenario where we have a different type of XYZ. Let's go to another region altogether to see if that's the case. Yeah, so you can see we do get variation there. So in this instance, we have a full density sounding file. So from there, the only thing to really talk about is going to be with this object store. We are capturing the zip files that we download from the Army Corps, but we're also, in our current scenario, what Fuse is doing is reading a folder structure that was derived from the original zip file. It's been manipulated to remove unnecessary data and to introduce enriched metadata. That doesn't really need to happen on the directory system itself. That should probably happen similarly in a Fuse eHydro zip file bucket, where those zip files, or where, well, let me back up a little further, where these scraped zip files have been optimized and then repackaged and posted back to the object store in another bucket. So this would allow the scraper to completely manage the changes and the spatial analytics on the data in those zip files, so that Fuse would never have to worry about receiving data that may not have been ready to be introduced to Fuse from the scraper. But also it doesn't have to worry about the data management either. It just needs to look for any files that are in the bucket and either read the resources directly from the compressed archive or actually buffer the archive, decompress it, and then work with the files at that level. So that's what's up for discussion right now is now how to integrate the new scraper architecture into Fuse so that it can actually ingress these data in an efficient manner. So we have some legacy things that we could probably get rid of. So thanks everybody. I look forward to the discussions.